Okay, today is November 14th, and we will continue the class. What we have done so far is to calculate detailed strain and stresses of each ply for the given in-plane and bending moment in the laminate with any layup sequence. It is very important. My screen is well shared. My voice and screen is okay. Okay. So let's briefly go through what we have done, and then let's run some cases using the Excel file we have developed so far. And last week, actually, we went through all the theory and developed an Excel tools. And now we can see you can calculate any stresses and strain of each ply for any given load. And as you can see, this is a brief, very brief procedures of the classical laminate theory. Again, I just like to emphasize again, this is the laminate with arbitrary layup angles. Okay, even any materials can be hybrid, like glass and carbons, and any material can be hybridized and with any angles, arbitrary angles, and then subject to an in-plane and bending moment. And then we know how to calculate off-axis strain, meaning each ply, and that strain is given simply like that. And on-axis stress or strain can be obtained by transforming the off-axis strain, right? Once we know the strain in each ply in on-axis of 5 directions, and we can simply multiply the stiffness, then we can calculate on-axis stresses. So that is the whole procedures. And in derivations, and based on the very important assumption is this: the strain, off-axis strain or ply strain is given in terms of the uniform strain all through laminate, and the curvature, linear distribution by the curvatures. So we have a 3-component in-plane strain and 3-component curvatures, and for the given load N and M, and we drive all the theory, and we come up with Abd matrix. So all we need to do is just invert, multiplying this matrix to a given load, and we get this in-plane strain curvature. And now we are able to get the strain of each ply. Okay, this is the very brief summary, but you need to be able to explain why you need to write down the procedures anytime, anywhere. So you need to repeat. You need to repeat writing, and you need to repeat thinking. That's very important. And these procedures, is relatively, I'm sure it's new to you, and I'm sure you understand what we do, but you need to make it yourself. To do so, you have to repeat, write down, repeat, think over and over. So again, let's take a look at the Laminate, I mean the Excel we developed based on those theory. Again, I just copy into here. So this is the ABD matrix. A, again, is the 3 by 3 because N is the 3 by 3, I mean the 3 components, and M also 3 components, and ABD and epsilon 0 and curvature. That is those are unknown, which we like to obtain. So once we have a ABD, as you can see, all you need to do to calculate the epsilon 0 and curvature, we just inverse and multiply. That's what we have done here. As you can see, ABD matrix. What is the ABD matrix? As you can see, this is ABD matrix, and load is this 3N and 3M, and it just inverse and then multiply. Then we can easily get these the 3 component in-plane strain and curvature, right? Now, once we have that one, what we like to do, I'm just repeating, okay? This is not the new subject, I'm just repeating. And this is the O-axis strain. Each ply we have a top and bottom, okay? This is the bottom and top, right? Bottom and top, K and K plus 1. As you can see, each ply we have a bottom and top, indicated by the ZK and ZK plus 1. So this is the bottom and so on. And then as we already know the strength distributions, and simply epsilon 0, 1, where this come from? Well, this is simply epsilon 1. So epsilon 0, 1 and curvature 1, these are needed, which is actually from comes from here. We just calculate by inverting this ABD matrix. So this is the first component of epsilon 0 and first component of the curvature. And again, simply because this is epsilon 1, you know, this ply has the epsilon 1 and 2 and 6 and top and bottom ply. And importantly, this is the a positions or height from the bottom and from the central axis to that ply, and the ZK has been already calculated from here. So this is a ZK, and of course this is the bottom and top. Bottom ply. Each ply the coordinate, and that can be easily calculated from known ply thickness, right? So ZK is coming from that one. As you can see, every equation is the same, right? For each ply, the variable is changing is the ZK, right? ZK is the one which is a vector, a table, a value along here. So each column we have a different ZK. This epsilon 1K for each ply is automatically calculated from bottom ply to a top ply. And same for epsilon 2. Epsilon 2 also epsilon 02 and epsilon K2. And ZK is the same, okay? So epsilon Z, and the K1 is the top surface of the that ply is the same thing, but difference it will be the ZK1, which indicates a position of the a top surface of this ply, right? Okay, so that is the O-axis strain. You know, O-axis strain. O-axis strain is these things. And so this one, this is O-axis strain. Now what we like to do is to calculate the own axis strain, the strain along the fiber and transverse direction and shear strain. So what we need to do is to just transform this strain. Epsilon 1 to 6 is basically epsilon 1 to 6. As you can see, 1 to 6 indicate of axis strain, and XYS is to indicate the of this guy, the on axis. So epsilon X is simply a transform the strain we calculate. This one is simply, for example, epsilon X is the first row, and multiply epsilon 1 multiplied by the M2. M is a cosine, and sine, as you can see here, see exactly the same. I mean, should be the same as this table. And we do the same thing for all other sorry, this guy, all other strain, right? All other strain transformations. And the here, one thing to calculate, how about the stresses? Well, once we have a stresses in this of axis, all you need to do is just multiply, as you can see here, epsilon bar is the of axis, and we know the of axis stress stiffness Q bar, and then we get the sigma bar is the of axis. So as you can see here, this is the matrix equations. So Q11, epsilon 1, Q12, epsilon 2, and Q16, epsilon 6. That's the first row, and for this sigma 1 and sigma 2. Okay, so we just went through, and then very importantly, the final output we like to use for next step is this on axis and on axis strain. Very important. The say here, okay, that is the strain and stress, okay, strain and stresses for the given. Okay, just 1 second. I like to have a new window and then arrange vertically so that we can see two windows. Okay, so this is the off-axis stress, on-axis stress, and off-axis strain and on-axis strain. Okay, so if we apply any load, this is automatically changing, as you can see, even for the moment. Well, we need to get used to this kind of distribution for the given load. So for a while, I highly recommend you to play with these values and how these strains and stresses are distributed for the given layup sequence. Currently, the layup sequence is a 0. I mean, this is the I would like to start with all 0, and 0 is the like that for the given uniaxial load, right? And then you can play with, say, what do you want to do? Say 45 and minus 45, and you know, all kinds of angle can be specified. Any angle. Very well-known angle is 0, plus, minus 90, 90, 45, 45, minus 45 and 0, and 0 and 45, minus 45, and 90, and 90, minus 45, and 45, and 90. This is very famous layup sequence. Is called quasi-isotropic. I will explain further why it is called quasi-isotropic laminate. Okay. I'm gonna delete this. Quasi-isotropic. I mean, here we tried several, cases. And I like to add some slide here. Okay, and I would like to say quasi-isotropic layup. Quasi-isotropic layup. In short, we just call QI. And what is that and why is it so important? Well, as you can see, we can, oops. We can layer, let's say 0, you have a 1 ply, right? And another ply, I'm gonna draw here. Another ply will be 45, like that. So this is gonna be a 45. And another one will be a minus 45. Minus 45 is like that. Minus 45. And by the way, minus 45 the same as what? 90 plus 45. And then 90 degree. So I'm gonna write down 0 plus minus 45. These are 2 ply, right? And then 90, and then symmetric. Okay, this is gonna be symmetric. If we plot them all together, it's like we have a 0, we have a 45, we have a 90, we have a 45, we have another 0, and so on and so on. So as you can see, you have a 0, you have a 45, you have a 90, you have a minus 45, which is equivalent to 135, and actually 90 is the 0 as same as 180, right? And 45 is the same as the this angle 225, and this and that one. So this is the again called a quasi-isotropic combination of a 0 plus minus 45 90. As you can see, the layup is angle wise is every 45, and so this as you can see, the each ply, the fiber direction is the important, and the fibers are, I would say, well distributed, right? Well distributed here, meaning every 45, the each ply is, the fibers are well distributed. So let's say this is a equivalent to certain load. Say any load everywhere, if the load can be applied to here and applied to here and or applied to here. Let's say we don't know where the load applied to. Apply, even bending or something. So the best way of the a random or unknown load, we can say a quasi-isotropic. And another important point is that here, the behavior-wise, the stiffness, stiffness is every direction is the same. It's a little bit difficult to understand. The stiffness is isotropic. Say you apply the stiffness in this direction or that direction, every direction, every direction, the stiffness-wise is the all same. So there is a equivalent stiffness. What is that? Let's try to calculate that one. But importantly, the stiffness-wise, the isotropic. It doesn't matter, independent of a angle. It's like isotropic material. That's why we call quasi-isotropic. Stiffness is perfectly isotropic. So let's take a look at the behavior using the Excel. So this is the quasi-isotropic. We can doubly repeat it, right? We doubly repeat it, and then where is the other one? Say we apply one direction. N1 is applied. This is so big. So this one shows the strain in the direction. This is the O-axis 1. And this is the strain in two direction and no shear strain. Now, let's say we apply, take a look at how much the strain we have. How much strain we have. Here is about the value-wise, about a 1.12, 10 to the minus 8. and then let's try to apply certain load. I mean, this is the this load. We have this and that and that and that, right? Now, let's say we apply any direction, like this way, any direction. And so this, I would say theta. So this load, this is the N1, and this is the some N node. Then we need to decompose this load to here and there. Right? So N, so N1 will be simply N times cosine theta, and N2 will be N sine theta, because the way we applying the in-plane load is has to be this direction, right? So let's say again, if we apply the load in any direction, say this is the one, right? This is the one as here. Then the N1, N2 needs to be this sine and cosine. So this one, I will change the this is the, I would say, load angle, say 45 degree, and N1, I'm write down this equation, equal 1 times cosine and radians of this angle. Okay, and N2 has to be equal 1 times and sine and radian, oops, sine, radians, and again this angle. Okay, so oops, not this one. No. Okay. Oh. Oh, sorry, I made a mistake. Okay, well, before we try this, what we need to do is that, sorry, I missed one step. Now, here is very importantly, this is the ABD matrix, right? This is the ABD matrix. And now this I'd like to inverse of this ABD matrix. This one is called ABD matrix, right? Okay, now we simply invert it. And very importantly, we get this epsilon 0 and the curvature, okay, and inverse of this and N and M. Now, how do we calculate the stiffness? How do we calculate the stiffness? Stiffness is simply when we have a materials and we multiply this load and sigma any stress, and we have a epsilon 1, then the E, that is a stiffness defined by this sigma divided by epsilon, right? So that is the stiffness. So how do we calculate equivalent stiffness of this layered laminate? Let's say, even though this is the laminate, we can calculate a equivalent stiffness and how much the strain we have. So we need to, from that, we can calculate the equivalent stiffness, right? So here, actually, to do so, we need to apply this N and epsilon, only this 3 by 3. This is needed. And for N, we need to divide by the H thickness, total thickness, so that we can calculate the sigma. Sigma is N over H. And then this will be, by definitions, epsilon equal 1 over E minus, always like that, right? That's the definition of compliance, right? That epsilon 1 and epsilon 2 and epsilon 6. So once we have this, we need to, let's call this is the S matrix. Okay, S matrix. And then S11 will be 1 over E. And so equivalent E is the 1 over S11. And now, how about the Poisson's ratio? Poisson's ratio will be, this is the S12 and divide by this. So S12 divide by the S11, and there is a minus. So this is the how we calculate a stiffness and Poisson's ratio. If we have another one, say 1 over E, say this is a different, epsilon 1 and epsilon 2 and so on. Epsilon 2 is the, epsilon 2 will be 1 over S22. This is the a definition of Young's modulus, right? So once we have an inverse matrix, and then what we can do, what we can do is that, say here, epsilon 1 equivalent and epsilon 2 equivalent, and even for epsilon 6 equivalent, and also Poisson's ratio, mu1 equivalent, and mu2, we don't need it. Only, let's say V1. This and that. Okay, only epsilon, Poisson's ratio in this way. So this one will be simply inverse of, this is the S matrix, so this one. And epsilon 2 will, I mean, Young's modulus 2 will be simply inverse of this one. And then epsilon 2 will be inverse of this guy. And this one is the minus a S12 divided by S11. Now, but as you can see, H has been missing. You know, we have to have a H because this is the N. So here, so this one, H was missing. So I would like to divide by H here. H, then this will be sigma. And then to do so, you need to multiply H here, right? So that H is the, so H multiply here and divide by H. So this can be a sigma. So we need to multiply H here. So here, H is what? We have, this is the H, total thickness. So we need to multiply by total thickness. And this one also total thickness. And this one also total thickness. And Poisson's ratio, it doesn't matter. Okay. So I'm going to just write down here. S is, this is the S. I mean, this is the S times, this is S. And S, we need to multiply I will say SH. So this is the epsilon 0 and SH. I'm write down this one, and this is the NH, and this is the A sigma. So SH, it will be sigma, and that is the say epsilon 1 equivalent will be 1 over S11H. Okay, that is the equation we used. Okay, so I'm not going to apply the load in every direction. This is the much easier way to confirm that. Sorry, I'm going to just apply that one and 0. Okay, so let's say, okay, let's say we layered the 0. First, let's try all 0. Okay, let's try all 0 layup. Let's try all 0 layup so that how this is calculate. All layup, and then let's take a look at how much. Okay, I'll put it here. How this equivalent to 1. Equivalent to 1 is that 0 means what kind of material we have here. What kind of material we layered. we layered a epsilon x and epsilon y. I mean, sorry, EX and EY and Parsons ratio and EX. That's the material we layered, right? This is the ply property, and that should be the same as the equivalent ply stiffness. Even we have a 16 ply, but the old ply have the same as this material property, own axis property. So this one has to be calculated as equivalent stiffness, right? 1 point. So as you can see, they are identical number. Right, 1.21 actually 121 gigapascal and 7.8 megapascal. I mean the gigapascal, right? So that is the exactly same as this material, right? Even same, okay. Parsons ratio, and this is the 2.09 is the shear modulus. Okay, so we confirm, we check this one. Now let's say let's try just a different 0.90, 0.90, and all 0.90, all 0.90. Now the material property wise, the E1 and E2, as you can see. Okay, I'm gonna write down this one as the value, and this was the 0 degree. Okay, now say this is 90, and this is the, I'm gonna repeat 0.90, 0.90, 0.90. You can imagine what kind of layup it is, right? 0.90, 0.90. Try to compare all 0. See, stiffness of this guy will be in this way, and that way will be the same, right? This in one direction and two direction, the stiffness will be the same. But the stiffness will be less than stiffness in this direction. See, this is the A12, and this is only 6. I mean, the 61 is a 121, right? So it's obvious because we have in this direction we have only half of this number of price, and the same for this. So as you can see, stiffness wise is almost half. Right, it's almost half, obviously, and so this way is almost half, but here even 90 degree we have a same stiffness because it's a 0.90 and 0.90, right? So it has to be same. Now, how about? But the point is that it is not the isotropic. You know, isotropic, to become isotropic, the shear modulus has to be, shear modulus always has to be isotropic, shear modulus has to be Young's modulus divided by 1 plus mu. This has to be met to be an isotropic. Right, so I'm going to just write down here, and the this equation 2 and 1 plus a Parsons ratio. And as you can see, it is certainly different. If that is not the same as this equation, then this is not the isotropic. Now we let's try 45 and minus 45 and 90 and 0 and 0 90 and minus 45 and 45. Oops. And this one, as I explained, it is isotropic. I said isotropic, right? Why is isotropic? Let's take a look at it. This E1 direction and E2 direction, they are same. And also shear modulus is the exactly given as this equation, meaning that this is isotropic. In isotropic, and we only have a E1 and Poisson's ratio. And shear modulus should be calculated from here. As you can see, it is, right? It is the same. They are same. So we can notice from this simple calculation, it is isotropic. So isotropic means that every direction we apply load, the stiffness will be the same. In real structures like airplane, they are using this isotropic layout a lot. But notice that this is the fiber directional stiffness 121 gigapascal, and E1 equivalent will be about what is that 44. So 121 versus 44. And how do we calculate? Well, approximately I would say this is the this one times 3/8. Okay, 3/8 is the magic number, and once you apply the 3/8, this value is the very close. Right, I mean close enough. So my point is that once you have a fiber directional stiffness, right? Well, how much the equivalent stiffness will be? Well, you can certainly use this kind of Excel sheet to calculate, but you can just roughly estimate very easily 3/8. Okay, so this is the that's the one I like to show you. And also another one I like to emphasize is that let's say we have this quasi-isotropic, or even any layup. Okay, any layup will be okay, and we have this kind of a layup sequence. We have a layup sequence, and we apply the load, and we now have a strain distributions like that. See, strain this is the important. We apply the N1. And certainly uniform strain. See, uniform strain. It is a uniform strain because it's simply all deployed. This is a 0, 45, minus 45, and so on. But that is attached together. they are expanding together, right? I'm gonna write down here. I'm gonna remind you that this is the what? This is the a force ply. This is the a force ply. This is a 0 degree, and this is the what? 45 degree, and minus 45, and 90, and you know, so on and so on. And all these strain have the same distributions, and for the obexer stress, of course, this 0 degree, this is a 0 degree. The stiffness is different every ply, right? This is the 45 and minus 45. This stiffness in this direction. So this one, I would say stiffness wise is this way, and this one stiffness is you know, stiffness this way and that way is quite different. That's why the stiffness is the jump like that. But the obexer strain is that even these guys 0 and 90, I mean the 45, they are all attached together. They are deforming together. So this is the just actually a bonded together. They are expanding together. So they are all experiencing uniform strain, and one direction and two direction and shear direction. Okay, but the obexer stress should be, I mean, they are quite different from ply to ply, mainly because I mean, it is due to a different stiffness. And now on-axis strain. On-axis strain means that the strain in every, you know, this direction and the this direction on-axis, but each one has the different angle. So this is the all on-axis strain. And the so this is a 0, 45, and minus 45, and so on. And obviously, the strain is also varying. They are different. And on-axis is also different. But this one is the simply Q, I mean sigma equal Q epsilon. This is the epsilon, and this is the epsilon bar, O-axis, and this is the epsilon bar and Q bar and sigma bar, right? So this one, epsilon bar and epsilon, I'm gonna delete this one. This is the epsilon. Oops. This is the epsilon. This is the epsilon bar, and this is the where? This is the epsilon sigma and Q and epsilon, right? So we have a 4 quantity, and from this O-axis to on-axis, what we need to do, we can multiply the transformations and epsilon transformation, and from here to there, we just multiply the sigma, I mean Q, and from here to there, we multiply, I mean the sigma and sigma bar is a transformations of the a sigma, but this is a there is a plus minus. Sigma bar is actually this direction, right? O-axis, and sigma is the on-axis. So this sigma, so we need to multiply plus. Plus means that this is the sigma bar and this is a sigma. We need to multiply the bar. But here, epsilon is different. Epsilon here, and the epsilon bar is this. Oops. Yeah. Epsilon bar. Yeah. Also, this is the A plus. And from here to there, we need to multiply Q bar. So they are all relate. This is this way, and of course we can go back by multiply inverse, and going back we multiply T epsilon and minus, and all relate, right? So to reach this quantity, we can this is the A value we get, right? This is the value we get, epsilon 0 and Z and curvature. So once we have this, we can come to here and there to reach this one. Or we can have this and that. They should be the same, okay? Please, it's important. Please do not get confused. To reach the on-axis stress, we can go to here and there, or we can transform the strain first, and then we can multiply the on-axis stiffness. And here, on-axis stress and on-axis so what we have done here is the stress is a transformed from on-axis stress. Transformed stress. So the one we have is this way. We get this Q sigma bar by multiplying Q bar, right? And then we transform. That's what we have done. That is what we have done here, right? Sigma, this is the Q1. So this is the sigma bar and Q bar and epsilon bar. And this is the Q is like that. So to reach this on-axis stress, we can just get this one. And another one is the, since we have an on-axis strain, we can have a sigma Q times epsilon. This is the epsilon, by the way, and this is the a transformation of the epsilon. Epsilon bar is the OBX strain here. This is the epsilon bar, right? OBX strain, and we multiply this, and we transform, and this is what you have. But again, as I said, this is the on-axis strain by the transform this one, right? But once we have an on-axis, we can calculate sigma by multiplying Q. We can simply confirm that one. On-axis strain, but now we are calculating by the Qxx times epsilon x, this is K, right? Plus, oops. Plus epsilon x y and epsilon x, I mean y here, and no shear because this is the on axis. And multiply here, and this gonna be x, y, and this gonna be y, and this gonna be y, y, and this gonna be y, okay. And this one, let's also copy and paste. And this one is what? Since this is the on axis, we don't have any material property, but only xs and s, right? Others are automatically changed. Okay, so and then let's try to this one. Now the Q1 and is 1, right? 1 and 1. And 1, okay. Now, as you can see, this value, on axis stresses, now calculated by the material property, not this one. Now, as you can see, try to compare. Are they the same? Yes, they are exactly the same. This one is calculated from by transformation of sigma bar, and this one is calculated by the multiplying the on axis stiffness. Is like that. We can calculate it this way, or we can calculate that way. Obviously, they should be the same. Okay. Now, so anyhow, we can play with any layups, any load. We can get the strain and stiffness in the on axis stiffness. Now, now like to point out how we can design. Design means that let's say we have a load, say 2-to-1 ratio load, or 1-to ratio load. And we, as a designer, we like to have what kind of a layer will be better. I said better. What do you mean by, what do we mean by better? We need to use this one now as the design tools. And as you can see here, the strain, and if we changing the any angle, the, as you can see, as you on the right hand side, the angle are very changing. I mean the strain is they are changing, right? Obviously they are changing. Then again, for the given load, we as a designer, how to design the angle? That's the key point. How? Well, first we can say, oh, we don't want stress too high, right? Stress means this on axis. Each ply, oh, we don't want this axis too high. So we design certain angle, right? We got a certain angle, and some ply reach higher, some ply get lower. You know, there are so many angles, so many to play with. How can you design? That's the one thing we like to know. we as a designer. See, this is the real challenging task. Okay, so again, designer-wise, for the given load, any load is okay. Any load is okay. We apply. This is the load, and how are we gonna changing or design the angles so that maximum stress can be lowered. Maximum stress should be low, not to reach the early failure, right? So that is the point. And so next subject, we will cover the failure, okay? Failure. When plan will failure? When plan will fail, and how do we detect the failure? So failure is very important for the designer. So to understand the failure behavior of each ply, then we can design. Next subject is to design. Okay. So I will skip this thermal stress. Okay, I don't wanna distract by this subject. More importantly, I like to cover the strengths. Strengths means failure. Okay, strengths means a failure subject, and we will define the price strengths and so on, and failure criteria. This is the main subject we like to cover today. Okay, like to have a break time for 15 minutes. It is 2:15, and let's get back to class at 2:30. Okay, thank you. See you soon. 오케이, 수업 시작합시다. So the failure, is that okay? The failure of the laminate is the fundamental, the basis of the design. So in chapter 5, we will discuss about the strengths of composite laminate. And I think considering the time remaining, may not be able to cover all these chapter 5. Okay, so I don't want to go above 4 o'clock. So sorry, I'm gonna change what we're gonna do. Actually, we need to, before we study about the failure, we will consider the temperature effect. That is as important as the mechanical load. Okay. What is the temperature effect? Let's get back to a stress-strain relation of the ply. Ply, of course, we have a strain and stiffness. I mean the stress, and we have a compliance matrix. What it means that, I mean, it's same for the isotropic. I mean, all material, as long as they are linear elastic, we have a strain and we have a stress and we have a compliance matrix. So meaning that the strain is caused by the stress, but the strain is also caused by the temperature dependency, because the strain is always a relative amount. So delta T is the a temperature increase or decrease with respect to a reference temperature. So there are a mechanical load, and there is another one due to a thermal load. So here we have a compliance matrix 3 by 3, and the delta T is the one quantity, just a scalar, temperature increment. And so this alpha will be a 3 by 1, same as the epsilon as a 3 by 1. So this is the strain stress temperature relations. And now we like to express this one using the stiffness. To do so, we move to a left-hand side. So strain minus alpha delta T, and then Q, actually inverse of the S matrix, that is the Q. And so this is the same form, but now we have a stiffness. Let's try to interpret the physical meaning. The strain is the this observed strain. This means a total strain, and this one is a total strain. And now minus the temperature thermal strain. Now this one is the, we can call a mechanical strain, the strain due to stress. So that's why we have epsilon minus alpha delta T, and then multiply Q and sigma. Both equations are often used in derivation, so we need to understand these two equations. Now, new material property, alpha. Alpha has the three terms, basically, meaning in each direction, x direction, y direction, and shear angle. So in other words, let's say we have a delta T, okay, delta T. So we apply the heat, okay, delta T. No mechanical load, only heat. What will happen? Well, it will deform something like this way, this much, right? Okay, let's assume this much. Now, this is amount in x direction, and this is the x directional amount. And also we have a y directional strain, that is this much. So alpha x is the x directional, alpha is called coefficient of thermal expansion, so CTE. So when alpha can be, composite, okay, alpha x is often mostly a positive, but can be negative because the carbon fiber is a slightly negative, has a behavior of the negative, shrink due to temperature increment. So depending on this material property, we have free expansions in every direction. And importantly, in shear, this shear alpha x is the 0, mainly, simply because symmetry. If this is the if this is the non-zero, positive, then this will be a strain will be positive, and then but we can just rotate and switch, and this as a negative. So they are contradict, and it's not doesn't make sense. So because of a symmetry, alpha s has to be always a 0. So we do have two different material property, alpha x and alpha y, okay, and they are called CTE. But in general, you can say that we have alpha s. So all the derivations we have learned in classical laminate theory, we now need to include these thermal terms. Okay, this is a new term which needs to be considered. This is on axis, and also off axis. We had these terms, right? We had this term, but we need to consider this a off axis thermal terms because let's say this is the material property, like this much alpha x and delta t, and this is the alpha y and delta t, and so on. Well, alpha s is mainly 0, right? Now in off axis means this reference direction, alpha 1 bar delta t, alpha 2 delta t, and alpha 3, the 6, is something like that, right? It's a simply strain transformation. So this alpha bar, and it's a strain transformation, so we will have a same transformation. You remember we have a strain transformations. So this is the alpha x, and this is the alpha bar, meaning whole this relation will be a minus directions. Minus direction means this is that way, right? This way transformation. So alpha multiply minus is this direction, and we get this. So we have a minus, actually minus epsilon. So this is already given. So this is how we calculate, how we transform the CT in off axis. Okay, with that information, let's try to redrive the laminate theory. Starting from this, and also very importantly, the off axis strain distribution is still given as that. Given is epsilon 0 and curvature. That doesn't matter whether there is a mechanical load or a thermal load. Always the laminate will experience the uniform strain and curvature. So by definition of the in-plane load, N is now given as the sigma bar dz. And now all we need to do is to consider these terms. And then instead of a sigma bar, we have a q bar, and epsilon 0, okay, epsilon bar. Now this is given, well, same as before. Now we have a new term due to our temperatures. And then integrate, and we already know epsilon 0 and curvature is the constant, so it's out of integrations. And notice that there is a z inside of integration. Now, very importantly, we have a new terms, q bar and alpha bar. Alpha bar is from this CTE and delta t and dz, okay? And this is the 3 by 3, and this is the 3 by 1. So this is the order of the 3 by 1 overly, same as n. So this is the kind of work act as the load. See, delta t is the external load, external value given. So as you can see, once we apply delta t, this will act as the mechanical load, which is similar to n. So we can this term, let's move to left hand side. So and then we can call this one as the nt. is from here. So n plus nt. So now A multiply B. A multiply, A, B, and epsilon 0, K, right? Now, moment is the sigma bar and Z, multiplied by Z, the same as before. Now, difference and new term we need to do is that this alpha bar and delta T, right? This is the new term. And we have a Z here. Let's try to integrate, same as before, and epsilon 0 and curvature is the constant, independent of the laminate. So integrate out of Z. Now here we have a new terms and Q and alpha bar and delta T, Q bar, alpha bar and delta T, and there's a Z here. And that is different from this. There is no Z here. Z actually comes from this Z. So this is the another new term, Q bar multiplied by alpha bar and delta T and Z. And also this whole term is 3 by 1. It's like moment applied, because we can move this one to left, and let's call this is MT. So when we have an external MT, notice that this is a material property, this is another material property, and then together with the delta T, it causes some kind of a mechanical, equivalent mechanical load on the left-hand side. Okay, so other than that, other terms are exactly the same, epsilon 0 and curvature, epsilon 0 and curvature, and B and D, and B and D. Okay, so this one, compared to this and that, this is the purely mechanical load, and this is the purely thermal load. Means that once we apply delta T, notice that we have this one will generate some equivalent mechanical load. So what we need to do is that, programming wise, we given delta T, how do we calculate this NT? And notice that Q bar times alpha bar. That's the one terms we need to have. This is not needed, and this is not needed. Okay, so once we have epsilon 0 and curvature, and now we A, B, D matrix inverse, and now N and M plus N, this is the thermal term, and mechanical bending thermal term. And once we have a epsilon and curvature, next step, which is a calculation of off-axis strain, will be the same as before, for each ply, and this is the off-axis. On-axis strain is the transformations according to that angle, ply angle. And then, very important, on-axis stress is to multiply the stiffness. Also, don't forget, we have a alpha delta T. So this one goes to here. We need to minus alpha delta T to calculate the sigma. In programming, we easily mistake. It is easily mistake to omit, drop this term, but don't forget these terms in programming, because this is a stress strain and temperature relations which we have started with, and then So this is the whole procedures. So we will have a on-axis strain and all the on-axis stresses as output for the given delta t. Okay, so very important. Well, everything is important, but let's take a look at this, some kind of a problem statement. Say we have a laminate. We have any laminate, any layup sequence. Now, instead of a delta t, we increase the delta t. Okay, somehow it may be due to a curing process. We may have a environmental effect. No matter what we say, we have a delta t. Then what will happen? Well, it may happen, sometimes bending like that. It may bending like that, and it may cause a lot of trouble inside the laminate. And then it sometimes break, it sometimes a break here, and sometimes a break there, and this kind of a deformation cause a huge problem in reality. So we should be able to predict exactly how much the thermal strain we may have. Okay, so and this kind of a derivation, I mean the deformation will certainly depending on this angle, ply angle, and all the ply angle and delta t may have a delta theta may cause this much, and another theta distribution may have a no bending. So point is that in addition to N and M, we may have a delta T as the this is the, I would say, load. And then we have all the layups. And then we have a epsilon 0 and curvature. Of course, that will give us the epsilon 0 and zk. And of course, we can have a ply stress. Now, next chapter, we'll see, because this stress, will they cause a failure? Are they okay? No problem inside? Well, that's the failure. That's important. That will be the next chapter. But here is the a problem statement wise. The load is the external mechanical load. This is the a mechanical load. This is the a thermal load. And the geometry wise, we have just a geometry is nothing but a flat laminate, right? Geometry is a simple, and also material properties, and we have a fiber and resin, and we have all kinds of a layup sequence. So this kind of a problem statement, and then we have all kinds of results, right? So this is a typical problem statement. We can start with, and then we need to find how these strains are distributed. Okay, so let's try to program again. Come back here, and back to and all you need to do is to get the equations. Okay, get these equations. So let's decide where will be the proper positions. Let's put it here. Okay, and this, as you can see, all you need to do is just calculate the NT and MT and these guys. So Q, right after Q, or right after B, ABD, and O-axis, we can, well, right after the O-axis stress, O-axis stiffness, which is Q, and alpha bar, this is the right positions. I think this is the right position. And we have a 3 component. So actually what you need to have is the, as you can see here, we need alpha bar. Alpha bar is not given yet. So we need some space for the, let's just call alpha 1 and alpha 2 and alpha 6. That's a sure. I mean, oops. Okay, so like to have these terms. Okay, that, oops. So that is, we can say, of axis, just, I would say just of CTE. Over CTE, and to do that, we already know how to calculate the of-axis CTE from there. So this is the, we're gonna use these equations. Now we need alpha S and alpha Y. Alpha S and alpha Y, that, you know, this, we start from a fiber and resin property, and we have a alpha F and alpha M, and we need to have a ply on axis alpha X and alpha Y. So this is the right place to calculate alpha X and alpha Y. In of course, this can be just given as a material property, right? This can be a given, and this is the material. In most cases, they are given. But since we are playing with the micromechanics, this is the these can be calculated from alpha X, I mean the alpha, fiber, and matrix. Well, that one actually we calculate you know, months ago, and I'm gonna get back to that slide. Actually, we delete the micromechanics worksheet. I'm gonna recall. Please, somebody has the micro on. Please turn off the microphone. See, this is the one we had in the early stage of a class where we calculate, did we calculate the alpha x and alpha y? Okay. Okay, this, remember alpha x and alpha y, and which you calculate given from a fiber and resin property, including alpha x, okay, right? And also this alpha y. Alpha y is a little bit more complicated, but we certainly have this equation. So we're gonna use these terms, and to do so, we need to start with alpha fiber and alpha M. As you can see in composite, the fiber has the CTE and matrix has a CTE. They are combined with the fiber volume fractions or matrix volume fractions, and we should be able to, well, I mean, the CTE in the ply will depends on these physical quantities, obviously, and that physical relation were derived. Now we do have an alpha y here, and also alpha m. Say this, let's double check, has the proper name, alpha f and alpha m, right? Okay, and the this is the VF, okay, and VM, and everything is given. And the I'm gonna copy these equations, right? And double check. Okay, fiber. Okay, this EXF has to be changed. We use the EXF. That is the little difference. And this one we VPF. Okay, VM alpha X. Okay. Okay. So we like to, where will be the proper positions for the alpha X? Well, this is the Q. We have alpha X and alpha Y because it's the on-axis material property. And this one, as you can see, where did it go? Here, I'm going to use these equations, okay? Here, I'm going to copy, but need to be careful. We have a EXF, EXF, and E instead of EM, we have a EXM. Well, matrix is usually isotropic, but we distinguish them in the, so EXM. I'm sorry, I wonder why we start with this. Okay, let me formula. Okay. Okay. Well, actually, matrix is always isotropic, but the fiber can be anisotropic. That's why we have EXF and EYF. They are different, but in most cases, the matrix is the isotropic. So I'm gonna change a little bit here. Okay, like to change. Well, well, I think it is okay. It should be okay. So here I'm gonna write down, this is the equation we already have, and then we can change it as EXF, and this is gonna be just EXM, okay? EX is actually, we already calculate. Oops, but we didn't, this is the EX, but I think we didn't, oh, this is the EX, okay. We use the underbar here. So this is the one, a alpha x, which we already derived, okay? And then alpha y, we already have the equations here. And the double check. Okay. Oops. Which one? Okay, alpha x. Oh, we didn't have a alpha x yet. I'm gonna give a name. And create from selections. Oh, okay, so this is the alpha x and alpha y. See, remember, these are all already derived in our class. I'm gonna show you where we cover that subject. Poisson's ratio. And this is the one we calculate alpha y and alpha This is alpha y, and this is alpha x. Okay, so that is the equation we already covered. That's why we have alpha x and alpha y. Now, of x's, alpha 1 to 6 is now calculated from this, and that will be the exactly, let's just, we can just copy the strain transformation, this guy. And here, so instead of this, what do we have? We have alpha x and cosine. As you can see, cosine and sine and alpha y. This is the alpha y and sine square. And then we don't have a shear term. Okay. And another one, we can just get these terms. Let me just copy and paste to here. And here, sine, but this one has to be alpha x, and this one has to be alpha y, and we don't have these terms. Okay, and then this last shear, so 2 times cosine and sine, and then if this is the minus has to be this one, and then this one. I mean, this one has to be alpha x. Oh, please follow me. This is gonna be alpha y, right? Minus and delete and enter. Okay, so this is the alpha 1. The reason there were, different minus is that this is the alpha 1 of axis. This one was a on axis, so it's a different angle. Okay, so we have alpha 1 to 6 ready. Now next one, as we know, these terms and t, where will be the good place? I would say here. I thought we have that term. We have say alpha 1 to less 1 2 3. Let's put it here, and then 3 terms ready. And this one, I would say the mechanical, no, thermal load. Okay, so this is the terms. How do you calculate? Well, I would say we call them N1 is called N. We didn't give a name. We can give a name. N1, 2, and so on. Now we can say this is the N thermal 1, N thermal 2, N thermal 6. Okay. Oops. So thermal 1 now where is the equations? Okay, here. This is the so what do we need to do? We need Q bar, right? So Q11 times, and the first term will be what? Aleph 1 times, oh, we didn't define delta T. We're gonna do that. And here is a DZ. DZ means ZK1 minus and ZK, right? That is the integration, right? When we integrate, this is gonna be a constant, and we need to have a ZK1 minus ZK. Okay, so enter, but we have to have a delta T. So delta T can be constant all over the ply, or delta T can be a different from ply by ply, because the temperature experience can be different. So let's say so this can, let's say dt, okay, dt give a name. So dt is the a ply, I mean the value for each ply, but right now let's say dt kind of a 0 constant value, and that is the say 10 degree. I mean say room temperature to 80, then is about 60 degree up, and this is considered as okay, I'm gonna give a name, and then this one say dt 0 and uniform dt. So all constant temperature is given, but later when you want to consider a temperature varying through the thickness, you can easily you can change these values, right? So that is the dt. So come back here, and we need to multiply here, say dt, right? So again, other term automatically dt there. And next, second term, what do you need? nt, n2. Now what can be done? This is the nq1. Wait. Sorry, we have a missing term here. Well, we have a lot of missing term here. And plus alpha 2 and 1, 2 and multiply. You know, simply Q bar time Q bar multiplied by alpha bar is the matrix multiplications, and Q bar and alpha 1, Q1, 2 and alpha 2 and so on, right? So that is the little mistake. And here 1, 2 and this is gonna be a 2 and same. And 6 oops, another mistake. We have a 1, 6 as well, and alpha 6 as well. We have a 1, 2 and 2, 2 and 2, 6, right? And here 1, 6 and Q 2, 6 and 6, 6. Okay, so this is the actually, as you can see, you need to have an integration. Integration means that you need to, did I give a name? Not yet. So this is gonna be a summations of a whole team, I mean whole terms here. And the same for here and same for there. And basically this is the one we can call them, we can name them as the and 1 to 6, right? And 1 to 6. Okay, now very similarly we can have about this one was that one. Now we have another term is this MT. So I'm going I just change MT and MT and MT and the let's merge them. So this term, now when we integrate, please take a look at this is a Z here, and when we integrate Z, this is gonna be a simply a integration of Z means square and square divided by 2, right? And here, same. And here, same. So that is the an equivalent thermal, I mean the thermal in-plane load and thermal bending moment, and also we can call them moment, and we can call them moment, right? We can call them moment, right? And then we give them a name, like that. So this load now, back to here. This was the just a mechanical load, right? And this one was calculated based on from this load. Now this is the load. I'm gonna have say oops, sorry. So I'm gonna have say here this one as that one. So S77. So I'm going to just S77. So oops. Just a T77 as that one. So just enter. And then I'm going to copy that one and paste to here. So this is nothing but this a thermal load, which you will calculate from this. And what I like to do is that this one has a name as the load, right? This name has the load, and oops, has a name as the load, and this one I like to give a name as the load. Load as the well, thermal load. Okay, so this one I just like to give a name like that, and then well, I like to. Okay, so this is the a thermal load. Thermal load, and all you need to do is to add that in addition here plus a load T. Please. Oh man. I hope it doesn't crash. Okay. Okay. This one needs to be changed as like that. Okay. And then enter shift. No. Control shift and enter. Oh. Okay, sorry. Oops. Okay, so this one recalculate, I mean, considering the thermal load. This is the from thermal load, and this is from a mechanical load. And this is the actually the temperature. Oops, temperature. This temperature is actually causing this load T, right? So I'm gonna. Okay, so we like to see what we can do this one. As you can see, I'm gonna have a plot for See, we have no mechanical load, but as you can see on the right-hand side, we have a strain distribution. What happened? Well, it's simply because we apply a temperature increase. If no temperature, obviously, there won't be any stress or any strain. But once we have a temperature increment of this whatever laminate we have, okay, let's try to start with, I mean, we have any laminate with any ply angles, arbitrary one, and then we increase the temperature 10 degree, and as you can see, OX strain and OX stresses and ONX and so on. So as you can see, this temperature increment, and please pay attention to how much strain we have and how much stress we have. And here, let's say easily 100 degree, and we can have a very high stress and high strain. Strain means that, well, not too much, but this one has the, 0.00114. So this is the amount and stress, we have this much stress and deformation. See, this has a slightly, has a slope. What does it mean? Slope means that we have a curvature. A curvature means it bend, right? In addition to an extension, it may bend. So again, the very important the behavior of the composites. So I'm gonna save as a version 6. See, once you fully understand the theory, the programming is, very straightforward. You as an engineer need to understand the theory, understand some algorithm, and understand how to program. That's the all. I mean, you need to have a capability of a programming. Without programming, just understanding the theory, you cannot execute. You cannot. You can be a good designer. Well, you can say you can use the commercial tools, of course, but using your own tool, you need to be able to understand and train yourself. You can be machine learning yourself, and then you can optimize yourself easily. Okay, so back to our previous midterm. I'd like to I assigned some load like 1 to 2, and there were no temperature difference. I mean, 0. And then we had several terms. I would say I'm gonna rearrange fiber directions. Have a X, oops. Okay, I'm gonna have a X, Y, and X. So we had the X and Y and S. Of course, K and K1 is the top and bottom ply and bottom surface. And also we had a defined the strain energy, meaning we apply the load and how much the energy. I mean, energy means always the load and deformation, and load and strain. So that is the one we defined. Okay. So last time we defined a ply, angle ply laminate. So this is the angle, and then this is gonna be a minus, always a plus minus and plus minus, and up to all the ply. So plus minus, if we specify 45, or 45 has the plus minus, and so on. If you want to make a symmetric, all you need to do is just change this one as the positive. I mean, then it's a minus, plus, and this much. And so this is the called a angle laminate. So as you can see, this is the actually angle. In this case, you can change the name, angle, and then angle, say, the 30 degree, and as you can see, plus minus, and again, the load is given like that. And please pay attention to how much overback strain and overback stress, and this is the how much, right? Very importantly, the on-axis stress is the same, because the all plus minus and balanced laminate. Then let's say see how much. I'm going to change it to a 45 and see what happens here. What is increasing, right? And see what happened to if I change it to angle to a 60. Why it has some variation. And on-axis strain in the fiber direction. Fiber direction will be important. And of course, this epsilon y is also important. And see how they are changing. I'm going to keep this guy at maximum. I'll say keep them as a constant and keep them as the constant, so that we can fix the coordinate. How to get rid of this? I don't like this. Okay, so when we change this angle, you can see more dramatically. It's small. I just fix this, maximum and minimum, so that you can see better. The angle 10 degree. See, 10 degree shear strain is really jump up. Try to visualize the angle. See, plus minus 10 degree. Oops. Plus minus, this is the plus minus 10 degree. This is the actually 1 and 2, this ratio. So 10 degree is very, small angle like that. And then shear strain is really high. Well, hard to explain, but you can see. And 20 degree, this goes up. 30 degree, oh, sorry, 30 degree and 40 degree. See, this guy is, let's see. While this shear strain is still very high, well, something is not okay. And then 60 degree. Just pay attention to the X and Y component. And 70 degree. Now you see the shear strain is smaller, but a transverse strain is high. You know, the transverse is very dangerous, and transverse means that the strain strain in this direction, right? If this direction is high, this will easily break in the matrix because of a matrix failure. And anyhow, okay, strain X is this, and the Y is the, oops, oh man, confused here. This one, we rearranged this one, and strain. Okay, so as you can see, the main point here is that whenever we change the angle, right? Whenever we change the angle, the strain, all the variables are changing, right? So we as a designer, how do we determine this angle? How do we determine this angle? So that's why we change this angle from 0 to 90, and see how they are changing. And this is the result. Okay, this is the result. I'm gonna separate the strain guy. The strain is not the same physics, so we get rid of it. And the like that, and double check. This is 1 to 2, and plus all 2, 3, 4, 2, 3, 4. Okay, that's good. Okay, so so this is what is it? Where is it? Oh, it says a strain. Okay, so this is the result we got. Remember, we have a load 1 to 2. We have a load as the 1 to 2. We have a plus minus. This is the angle theta, and this is a minus theta. And we apply the N1 as the 1, and this is the N2 as the 2. Well, why I prefer a 1 to 2, I'm going to explain the next class. But anyhow, this much load, and we changing this angle. See, this is the angle, And this is the what? Strain, right? Strain of each one. We have a strain of this one. While we have a many ply, but the maximum, we may have another ply, this one. We already have a distributions of that, all the strain, right? On-X strain. As you can see, I'm gonna just, 45 degree, okay, 45 degree. Let's take a look at the strain, 45. How much is this? Can you see that? How much is this? 1.11, 1.11. I'm gonna get rid of this. No. Cannot click that one. Axis. Now I'm gonna have a automatic. Okay, so this one. So they are changing. The point is that they are changing, and this value and then maximum value has the distributions like that. Okay. So how much angle we have right now? We have a 45, and go there and 45. We have a 45. We have a 45 here, 45, and the X, get rid of this for a while. 45, and how much? This is strain X has the, this much, 1.1, about 1.1 10 to the 8. And here, this guy, what happened to, they are overlapped. So here, the strain is this guy is a 1.1 and 10 to the minus 8. So this is the line, actually the same. On-X is X, and this is the distribution. This is the happen to be maximum, and this is the angle we got from here. And now, as you can see, if we change the 50, we change it to 50, and you can see the strain is about the 1.2, and strain X is the blue, and that this guy is the about 1.2, right? So I mean, it's obviously these distributions gives us the strain along angles, and it sometimes reach the maximum here at 40. What doesn't mean it reached the maximum at a sigma epsilon X at the 50 degree, and energy wise is the almost the minimum. And others, I'm going to replot. We have this. Okay. Others like there is no y here. Okay, we have a y here. Yes, I'm gonna delete this. So we have a strain X here, it reaches maximum, and the strain Y is reach the minimum about the same angle, like a 50, and the shear strength is behavior like that. So again, each one, say this is the A theta, and this is the epsilon X and epsilon Y, and this is the all the shear. So for the given load, N1 given as a 1 and N2 given as a 2, but we changing this angle. We change this angle, and this changing angle, alpha x sometimes distribute like that along the alpha, theta, right? And the strain energy is like that, and strain Y is like that, and strain S is like that. Again, let us ask questions. Which angle theta is good? Good means that we should not fail. We should not have should support strongly and with a minimum weight. Which angle is the good? Well, we don't know. There are so many response, strain X and strain energy, or strain Y. Well, strain YY is really zero, and this one is also really small. What does it mean? And this angle, and that angle, I hope they are almost the same. And this angle, the fiber strain is really high, but this epsilon Y is almost zero. So it's like all strain is along the fiber. This is good. Why? Because the fiber takes over all the load. Even though it is reach the maximum, but this is a fiber and can take over the load. And look at this, strain Y. Strain Y is in this direction. This is very weak. It may fail very quickly because the matrix cannot support much the load. So the strain Y-wise, the angle, certain angle strain is really high. So which may not be good. We don't know yet, but this may cause some problem. Okay, so the point is that which angle needs to be designed. Well, we don't know yet. That's why in next chapter we need to understand the failure theory, like Van Mises stresses. We need to understand the when ply will fail and weaker than other case. So that's the subject we need to cover next week, the strengths. Okay, that's the strengths. And that's the one we're gonna we will study. This is you can say the second part, which is very important. So far we discussed about the stiffness behavior, but now it's the strength behavior. Strength behavior, and again, depending on the layup sequence, we have so much complicated strain, stress, and overexes and so on. Which one will fail? Which one is the which one we have to take care? We don't know. It's complicated. That's why we will have a failure theory. Okay. Okay. So I like to complete the class before the 4 o'clock. Now it is precisely 4 o'clock. Okay. If any questions, and please share your questions through the cutoff. Okay. So that's the end of class, and I hope that I will again share all the this is gonna be a version 3, new one, not much change, but the one we just developed for Excel is very important. I'm gonna certainly share this one, okay? But today I'm not gonna share my Excel. You have to develop. You have to develop. You need to enter. You need to consider this thermal load, and for that purpose, you need to have an alpha X and alpha Y and so on. And this save as okay, today was a version 6. Okay, so version 6, I'm not gonna cover today. You need to now develop, extend the one you have, okay? And then I'm gonna assign the homework now, okay? Which will be due next Friday. Okay, thank you so much, and then see you next week. Bye.